There is an unresolved mystery at the foundation of mathematics. When plotted on a standard number line, the distances between primes appear entirely random. To find a pattern in this sequence, mathematicians and data scientists frequently map these numbers out of a single dimension and into higher dimensional spaces, looking for a hidden predictive formula. Here, primes are plotted on a complex polar scatter plot. Angles are determined by the golden ratio, and radial distances by the inverse of the prime gap. Small gaps cluster tightly in the center, completely surrounded by a sparse outer ring of larger gaps. This geometric transformation creates a highly structured macroscopic pattern, but it is a heuristic illusion. It does absolutely nothing to provide a deterministic formula that can predict the next prime number. To actually predict prime numbers, we have to discard spatial geometry and attack the exact sequence of the gaps as raw data. This brings us to the core experiment. We'll treat prime gaps exactly like an empirical dataset and run them through a modern data science pipeline. We will test whether statistical algorithms and ensemble machine learning models can find the mathematical rules that spatial geometry missed. If machine learning can predict these gaps, it solves a centuries-old problem in number theory. If it fails, the precise mechanics of that failure will reveal exactly why primes operate the way they do. The experiment begins with a probabilistic baseline. We first attempt to fit standard probability distributions to the raw frequency of the prime gaps. This chart shows prime gap distributions up to 1,000. Overlaid are a Poisson curve and a geometric curve. The Poisson model captures the average rate, mapping the dense cluster around 6. The geometric model traces the long tail of larger gaps. To test the accuracy, we run a Kolmogorov-Smirnov test. The results return extremely low p-values, 0.0002 for Poisson, and 2.83 times 10 to the negative 14th for geometric. In statistical validation, p-values this low definitively prove that the prime gap data does not naturally originate from either of these standard distributions. A mixed probability model can mimic the local frequency of gaps on a graph. It fails to explain the underlying mechanism generating them. Since static frequencies failed, the methodology shifts to sequential modeling. We introduce Markov chains, which attempt to predict the next gap based strictly on the state of the current gap. This is a transition matrix heat map for prime gaps. It displays probabilities of moving between gap sizes, highlighting common transitions in these diagonal cells. This diagonal dominance reveals a pattern. Small prime gaps are frequently followed by identical small gaps. To validate this sequential model, it must be extrapolated and tested against a new, larger dataset of primes strictly greater than 1,000. The model completely breaks. The KS test comparing the Markov simulation against the new dataset returns a p-value of exactly 0. Looking at the data shift, the simulation's mean gap holds at 5.96, but in the higher dataset, the actual mean gap jumps to 8.44. Markov chains fail at scale because prime gap growth is non-stationary. As numbers grow, the gaps stretch out logarithmically, instantly breaking any static probability matrix. Because simple probability models failed to scale, the core experiment must escalate to nonlinear ensemble machine learning architectures. We deploy a decision tree regressor, an algorithm explicitly designed to learn the complex nonlinear rules dictating sequences. This chart tracks mean squared error. The initial decision tree sets a high baseline of 16.99. We upgrade to a random forest model, reducing variance, and the error drops to 16.01. Finally, a gradient boosting machine pushes the error down to 15.59. While these ensemble models successfully reduce the error margin, the predictions remain stubbornly inaccurate. Standard regression features are simply not enough to crack the sequence. This forces the use of the ultimate tactic in applied data science, feature engineering. This is where deep domain expertise is injected directly into the algorithm. We feed specific theoretical inputs into the model, expanding the dataset with modular arithmetic properties and prime number theorem approximations. Then we add the most advanced feature available, mathematical approximations of the distances to the Riemann zeta function's non-trivial zeros. This is the result of the highly engineered gradient boosting machine. The prediction error doesn't drop, it plateaus and actually rises to 16.46. This is the core anomaly. Injecting profound theoretical mathematics provided absolutely zero new predictive utility to an optimized algorithm. This stagnation represents a fundamental limit in predictive modeling. AI cannot brute force a prediction out of prime gaps because the gaps themselves do not rely on local feature interactions. Why did an optimized machine learning model, armed with advanced number theory features, completely fail to predict the next prime gap? It comes down to the operational nature of machine learning. These models optimize strictly for local statistical variance. They search for localized, repeating interactions between nearby features. Prime numbers operate differently. They are strictly deterministic, yet their distribution perfectly mimics pseudo-randomness on a local, observable level. Prime gaps are not governed by localized interactions. They are governed by profound global analytic structures that dictate the entire number line at once. This overarching global structure is the spectrum of the Riemann zeta function across the complex plane. The non-trivial zeros on the Riemann critical line map directly to the exact distribution points of primes on a standard number line. Applying heuristic regression to primes proves that pure mathematics requires global analytic proofs. The mysteries of number theory cannot be solved by the local statistical approximations of modern AI.